The first thing you need to be able to do for the exam is to do some binary conversions, and most of you guys are really good at this anyway, so I don't think this will be a big deal. So the first thing we need to think about is the fact that binary is a base 2 system. So that means there are two symbols, and those symbols are 0 and 1. So they're the only symbols that you can put in to a column in binary. So denary, sometimes called decimal, is a base 10 system. And as you know, you've got ones, tens, hundreds, thousands. So you can put any number between 0 and 9 into the columns on a base 10 number system on decimal. This is the numbers you've been using kind of for most of your life, really. So if I wanted to represent 21, I'm saying that that's 2 tens and 1 single unit, 21. If I wanted to represent that same 21 in binary, then just like I've got 0 here in the thousands column and 0 in the hundreds column, I'm just going to start on this side and say that there are no 128s or 64s or 32s that actually go into 21. But 16 does, so I can have a 16, and that's going to leave me 5 left. So if I wanted to do it formally, I could just do the takeaway sum and say that I've got 5 left. So there are no 8s that go into 5, but there is a 4, and I've taken 4 away, and now I've got 1. And so there's no 2s in that, but there is a 1. And so my binary representation for 21 is 0, 0, 0, 1, 0, 1, 0, 1. So we might need to convert a binary number back into a decimal number. So the way we can do this is just if we put the headings at the top, that really helps. So remember, in binary we've got 1s, 2s, 4s, 8s, 16s, 32s, 64s, 128. So we are just as powers of 2. We're just putting those numbers in there at the top. So then what we're looking for is 1s, because this will say 1 times 32 plus 1 times 8 plus 1 times 4. And if we add that up, we get 32 and 8 and 4, which is 44. And so that first number is 44. Then the second one, we've got 32, we've got 16, we've got 2, and we've got 1. So we add those together, 32, 16, 2 and 1, and we get 51. Now it's worth noticing that if you've got a binary number that's got a 1 on this end, that's going to mean it's an odd number, because it's the only way you can have an odd number is to have 1 in this 1 column. So that's something else you can look at. Just to when you're looking at the binary number, if you've ended up with an odd number when there's a 0 in this column, then you must have made a bit of a mistake. So you have to go back and have a look. So adding the numbers together, sometimes we can add binary numbers together. Now I've done these in base 10, but I can add in binary. I don't need to worry about those numbers. So if I say 0 plus 1, well, that's obviously 1, and 1 I can put in my column because I can put 0 or 1 in each column. So I've got 1 here. 0 and 1 is again 1. 1 and 0 is again 1. 1 and 0 is 1. 0 and 1 is, well, it's 1. And 2 ones is a 2. Now I can't write down a 2, but I can write a 0 here and carry a 1, because the pattern for 2 in binary is 1, 0. So I'm carrying my 1, and I've got noughts here, but there's the 1 I've carried, and I've added my numbers together. So easy enough to add together binary numbers. If you've got something you can put in the column like a 1 or a 0, that's fine. If you've got a 2, you need to do a carry because you can't write 2 in there. So if we work all this one out, we will come up with the same answer as if we added these together. Now what about if we have to add more numbers than that? So I could try adding all 3 of these numbers together. So I'm going to try adding these numbers together, and so I've got 1 and 1, and as we discussed, that's 2, but we can't write 2, so we're going to put 1 and 0. So then I've got 1 and 1 plus the 1 I've carried. Well, now I've got 3. So if I've got 3, the binary pattern for 3 is 1, 1, 1, 2, and a 1. So I'm going to put 1 in here and carry my 1. And again, I've got 3. I've got 3 again. I've got 3 again. And again. Now I've got 1 plus 1, which is 2. So that's 0 and carry 1. There's nothing in this column, so just the 1. So I'm going to end up with 1, 0, 1, 1, 1, 1, 1, 0. So that's adding together binary numbers. So the thing you need to remember is that if you can't write anything apart from a 0 or a 1 in these columns. So if you get to 2, you've got to then carry 1 into the next column. So we're carrying it into the 2's column in that case. If you get to 3, then you're still carrying 1 into the 2's column, but you need 1 in your column that you're working in to make it 3, because the pattern for 3 is 1, 1, and the pattern for 2 is 1, 0. Okay, so here are some for you to have a go at. So have a go at these. You can pause the video and have a try at adding these together. You can then have a go at converting these as well. So pause the video, have a go at these, and then we'll come back and have a look at how to do them. So pause the video now. Okay, so hopefully you've had a go at those. So if we look first at adding these at the end, so I haven't put the number positions in. I don't necessarily need to, but always remember that you could do so. You know, there are 1, 2, 4, 8, 16, 32, 64, and 128. So you can put those in if you want to, but just to add the binary numbers, we don't necessarily need to, because we can just add our 1s and 0s. So 1 and 0 is 1. 1 and 0 is 1. 1 and 1, well, that's going to be 2, but we can't put 2. But the pattern for 2, remember, is 1, 0. So we're going to put 0 and carry 1. I've got 1, 0, and my carried 1, which is 2 again. So it's going to be 0 and carry 1. 0, 1, 1. Again, it's 0 and carry 1. Now I've got 1, 1, and 1. Well, 1, 1, and 1 is 3. The binary pattern for 3 is 1, 1. So 2 and a 1. So I'm going to write down 1 and carry 1. I've got 1 and 0 and 1, which is 2. 0 carry 1. And then 1. So my final answer is going to be 1, 0, 1, 0, 0, 0, 1, 1. So hopefully you got that one right. So then the slightly more tricky idea of adding together 3 binary numbers. So this is the most that you'll ever have to do, really, is adding together 3 binary numbers. So I'm starting on the right hand side. I've got 1 and 1 and 1. Well, that's 3. And as we know, the binary pattern for 3 is 1, 1. So we're going to put 1 and carry 1. 1, 0, 0, 1 is 2. 0 carry 1. 1, 0, 0, 1. Again, it's 2. 0 carry 1. 0, 0, 0, and the carried 1 is just the 1. 0, 1, 1. Well, that's 2. So again, 0 carry 1, because remember that the binary pattern for 2 is 1, 0. 0, 0, 0, and the 1. Well, that's just 1. And then 1, 0, 0. Again, we're just 1 and 0. So our final answer for adding those 3 numbers together is 0, 1, 1, 0, 1, 0, 0, 1. So that's adding together 3 numbers. So hopefully you did okay with that one. So maybe we could think now about converting. So we've got a couple of numbers here to convert. Converting 52 to binary. Well, we need our binary positions. So we'll just write those down. And on your exam paper, it's always best to either write them down on the paper if you can, or if you don't have a paper and it's electronic, then write them down on a piece of spare paper so we don't make any mistakes. So I got 52 in order to do my conversion. Well, there are no 128s in 52, so I can immediately write my 0 there. Same goes for 64, but there is a 32. So if I do a subtraction, I'm going to end up with 20 left. So there is a 16, and I can take my 16 away. It leaves me 4. Here's my 4. I've got nothing else left. So that's my answer. I've converted 52 into binary. So if I do the same thing with 66 over here, that you hopefully have had a go at. And again, I'm just writing down my positions. I don't want to make a mistake, so I'm going to make sure I've got all of my positions correctly written. And the number this time I'm doing is 66. So I'm going to write that down at the side. So there are no 128s, but there is a 64 this time. So I've got 64. I'm going to take that away. Well, it only leaves me 2 left. Well, that's actually quite nice and easy for me to do this one, because I've got all of these are going to be zeros because none of those fit into 2. But I do have a 2, and that takes me to 66. And that's the answer to converting 66 to binary. Hopefully you got those right. If you didn't, set yourself another couple of practices. You can always check back to see if you've done it properly, so you could just add them together. You know, we've got 64 plus 2 is 66. In this case, 32 plus 16 plus 4. So we can do that as an addition if we want. 32 and 16 and 4. 3, 4, 5, 52. We carried the 1, and that just checks for us that we've done it correctly. And there's nothing wrong at all with checking back, reconverting and checking back on your exam when you're doing the exam. So in this one, we're just going to look at the idea of overflow. So there's an overflow error, or overflow occurs when there's not enough bits available to represent the number that we want to represent. So if we did the addition that we've got here in binary, 0 and 1 is 1, 0 and 1 is 1, 0 and 1 is 1, 1 and 1, remember, is 0 carry 1, because our pattern for 2 is 1, 0, and then we've got 1, 1 and 1, which is 3. That's 1 and carry 1, because the binary pattern for 3 is 1, 1. 1 and 1, and our carried 1 is 0 carry 1. 1 and our carried 1 is 0 carry 1, and 1 and our carried 1 is 0 and carry 1. So the answer that we've got is now 16, 20, 22, 23. Well, 23 is not the correct answer for adding together these two numbers, because it can't be, because we started off with something in the 128 position here. So an error's occurred, and that's the error. We lost that bit off the end. So it's called overflow if you don't have enough bits to represent the number that you want to represent. And you might remember that in 8 bits, the biggest number we could represent is 255. So if we get a number that's bigger than 255, we can no longer represent it in 8 bits, and so we would get an overflow error. Now, of course, in the real world of computing, we tend to have much larger registers than 8 bits, so we can represent much larger numbers. But as far as we're concerned, when we're trying to describe an overflow, it's when we don't have enough bits available to represent the number, or the size of the number that we want to represent. So on this video, we want to talk about hex. So hexadecimal. So hexadecimal is a base 16 number system. Computers do not read hex, but humans read it very well. So humans quite like to use hex because it's a shorter notation, and maybe we'll see why that's the case in a while. So we've got base 16, so therefore we've got all the symbols 0 to 9, which are nice, and they're just 0 to 9. In the same way, so 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. But then we've got some other symbols that we need to make up to 16. So A becomes 10, and we use B for 11, and C for 12, D for 13, E for 14, and finally F for 15, because we've now got 16 symbols, F being 15, and we've still got 0, so 0 to 9 and A to F. So when you're doing a question in the exam, I always think it's better to just write down this table like this to say, I've got A's 10 and B's 11, and I know we could just remember it in our head, but actually it kind of prevents us from making mistakes. So I always like to see that written down, and I would do it myself just to remind me what I'm doing. So maybe we would do a conversion. So perhaps you might get a question which says something like, convert the hex number FA into binary. So into binary, we could do this. The way that we could do this is simply just by writing down our positions, and each 4 binary positions represents 1 character in hex. So my character in hex, you can represent it by these 4 binary digits, and the reason for that is that we've got 16 different combinations of binary numbers in 4 bits. So if I was to represent A, I'm looking up on my table over here, A is 10, so I've got 1 8 and 1 2, and that's 10. So that's my first bit of representing A. So then I also want to represent F, so I'm going to write down the same numbers, 8 4 2 1, and F, if I look up on my table, is 15. So to represent that, I need an 8 and a 4 and a 2 and a 1. So my whole number is 1 1 1 1 1 0 1 0, and that's just representing a number in binary when you've been given it in hexadecimal. So we're just converting from hexadecimal into binary. So here are some hex conversions for you to have a go at. So there are 4 here for you to have a trial at. So if you pause the video now, then you can have a go at them, and then you can start it up again and have a look at the answers. So pause the video and have a go at these 4 conversions. Okay, so hopefully you've had a go at those now. So you'll notice on the right hand side, of course, I've written down my positions again. So I've got A is 10 and B is 11 like this, just to remind me of what they are, and just to remind you that you can do that in the exam or on some scrap paper or whatever you want to do to help you and to try to prevent you making any errors. So the first one, A4, remember I'm going to do my numbers 1 2 4 8 here. So I'm going to convert 4 first of all, which is going to be 0 1 0 0, because this is the 4 position. I'm going to do the same thing on this side, 1 2 4 8, and A, I'm looking up on my table here, is 10, so I've got 1 8 1 2 and a 0, so that would make 10. So my whole number converted is 1 0 1 0 0 1 0 0, and that's A4. So if I move over to this one, which is 9F, then it doesn't actually matter which order I do these in. I could do it this way. So if I do the 9 first this time, I've got 1 8 and 1 1 to make a 9. So 1 0 0 1 is a 9. And then I've got my F on this side, 8 4 2 1. And I need 8 and a 4 and a 2 and a 1. And that's 15. So actually, anytime you've got an F as a pattern, then you might remember that that is 1 1 1 1, because it's the biggest number we can put in those 4 bits. I'm moving down to this one. I've got D8, and I'm going to do exactly the same thing, 1 2 4 8. And in this case, we've got 8, so there's an 8 there, and the rest of these are going to be zeros. I'm going to do the same thing on this side, put my numbers down for D. D, if I look up over here on the table I've written, is 13. So I need an 8 and a 4 and a 0 and a 1. 8, 4 and 1 is 13. So my whole number, 1 1 0 1 1 0 0 0. So then I've got A and B. So I'm going to do exactly the same. B, if I look up, is 11. And that looks like that. An 8 and a 2 and a 1. And A is 10. And so that's an 8 and a 2. So 1 0 1 0 1 0 1 1 is the actual answer to that. So hopefully you got all those correct. So on our whole binary number, we'd end up on this one, for example, with 1 0 1 0 and 1 0 1 1. So if you needed to convert that into decimal, you could do that just the same way as we did before. 1 2 4 8 16 32 64 and 128, and then we can just add those together. 128 because I've got 1 in that column, and a 32 and an 8 and a 2 and a 1. And we converted it just by adding them up. So that is 171, and that would be the way to convert from hex all the way into decimal. Hopefully you got those all right, and if you didn't quite get them right, set yourself up a couple more to have a go at. You can always check them. You can check them by looking at the table that you've got here on the right hand side, which is showing you the numbers. In fact, you could just decide that all of those you could represent in binary if you wanted to. So if you said A was 10 and that the pattern for A was 1 0 1 0, you could write yourself a whole table like that and then check them out. So this is a little topic that we may not have got to actually. So very straightforward. We're using a code scheme to represent letters. So when the computer, as you know, represents anything, it has to use binary numbers because it can only respond to ons or offs or switches. So we looked at that as an idea. So one way to represent text is called Ascii, and that stands for American Standard Code for Information Interchange. You don't need to remember that, but Ascii is the code scheme. What you do need to remember is that it uses 7 bits. And if you remember, a bit is just one binary digit, so that's a 0 or a 1. So if you had 7 bits, you could have these positions: 1 2 4 8 16 32 and 64, because there are 7 of them: 1 2 3 4 5 6 7. So if we added those up, the maximum number we could have is 127. And if you look at the code chart on the right hand side of here, the biggest number here is 127, and that represents a strange little square as the character. Only ones we're really interested in are these ones here, which represent letters. So if you look, we've got Ascii 65 is a capital A, and Ascii 66 is actually a capital B. And so if you, for example, got the question, given that Ascii 65 is A, then what would Ascii 68 be? So you only have to think about doing 65, 66, 67, which is going to be a C, and 68, which is going to be a D, because they just follow on numerically. And you can see that on this chart. All of the capital letters are between 65 and 90, with Z being 90. So if you get asked this question or something similar to it, then, if Ascii A is 65, what is Ascii 68 or 69 or 70 or 71? You've only got to count and keep counting up and saying that it represents whichever letter of the alphabet you've arrived at. So that'll probably be enough for you at this stage to know about. So you can see on this chart, there are lots of other symbols that you can use in Ascii, as well as uppercase letters. There's a whole set of separate character codes for lowercase letters, starting here at decimal 97 and going on down to 122. So the biggest number we can get in this 7-bit code is 127, but we do have 0 as well. So we've got 128 options. And the ones we're really interested in are the letter codes.